Swayam Prabha. Digital India. Educated India.
Friends, welcome to the 25th lecture on advanced steel design, where we will continue to discuss some more examples on plastic analysis and of course the application of analysis in design perspective. I will put as 2 because it will be a continuation of the last lecture what we discussed. In the last lecture, we are trying to apply kinematic theorem for a frame example to find the true collapse load. Okay, this was the problem where a frame is subjected to a lateral load of W and a vertical load of 2W at an eccentric portion of this. Okay. So, we computed from the beam mechanism that my collapse load is 9 MP by 2L. We also did the sway mechanism where we said the collapse load is 2 MP by L. We further went down to understand there are 5 possible locations where the hinges can form, but we need only 4 for a complete mechanism. So, we wanted to be sure using iteration procedure where this hinge will form. For A and D they are sure because they are fixed supports. Okay. So, now the hinge can form either B, C or E. So, we have a doubt. So, we are going for an iteration to find out the true collapse load. We started doing this and we said that the hinges will form at A, E, C and D. It is an assumption. Okay. The hinges will form at A, D, C and E. It is an assumption. Okay. We are assuming this. The external virtual work is force into displacement. So, 2W into del and W into delta. The internal virtual work is MP of alpha, which is at A. I will just do a different color so that we can check it. MP into alpha, which is at A. Then again there is a hinge here at E. So, MP into theta 1 and theta 2. Okay. This is at E. Then again at C you got 2. One is MP for alpha, other is MP for theta 2. And we do know that these inclinations will not be equal because the load is eccentric. Okay. It is not in the concentric position of the beam. Then the fourth one is MP alpha at D. So, this gives me an internal virtual work. Let us say this is equation number 1, we will take this 2. So, we want to equate 1 and 2 and find out the true collapse load. But there is a problem here. Equation 1 has got 2 variables del and delta, and equation 2 has got different variables alpha, theta 1 and theta 2. Okay. This is the issue what we had. So, then we started working out from the figure alpha will be delta by 2L. Okay. This is very simple, straightforward, and theta 1 and theta 2 need to be found out. So, now theta 1 cannot be this way. So, let us try to correct this and go back. Okay. So, we will simply say that the correction is going to be there for this case and let us do this. Okay. So, now alpha is delta by 2L, theta 1 is 3 del by L, and theta 2 is 3 del by 2L, okay, from the geometry. So, let us call this equation number 3. So, from this equation we can also say, trying to look at theta 1 and theta 2, we can straight away say theta 2 is theta 1 by 2, is it not? Because 3 del by L is theta 1, so theta 2 is theta 1 by 2. Okay. Now, for the frame to sway, towards right and maintaining this angle as 90, if this is alpha and this is theta 1, the frame has to sway towards the right. So, let us assume that the sway delta causes symmetric rotation at B. What does it mean? This is delta. Okay. So, we say now theta 1 is alpha. So, we are maintaining this angle 90 degree. So, this is true. Okay. Now, we already know the internal virtual work from equation 2. Let us copy that equation. So, internal virtual work is MP times of 3 alpha plus theta 1 plus 2 theta 2. Let us see this equation. Okay. So, which will be MP times of alpha is here. So, 3 times of delta by 2L plus theta 1 is already alpha. So, can I say this is alpha plus theta 2 is 2 times of, let us say theta 2 is theta 1 by 2, which will become MP times of 3 delta by 2L plus alpha plus theta 1, which I can now say is MP times of 3 delta by 2L plus alpha, because we have this equation here. Okay. So, now I can say internal virtual work is MP times of 3 delta by 2L plus 2 alpha, which is MP times of 3 delta by 2L. Let us try to find out alpha in terms of delta, which is delta by 2L. So, can I say this as 2 times of delta by 2L, which is MP times of 5 delta by 2L. Equation number 4. Okay. I have modified the internal virtual work in a simplified form. Look at the external virtual work, there are 2 variables, okay, but we know they are connected to each other. Okay, they are connected to each other. So, let us try to do that. So, let us say external virtual work, which was 2W into del plus W into delta, which can be said as 2W del, we already said is 3 delta by L, okay, and delta is theta 1. So, theta 1 L by 3 is it del, is it not? Okay, plus W times of delta, which is 2L of alpha, 2L of alpha, okay, which will now become 2W theta 1 L by 3 plus W 2L theta 1, because we know alpha and theta 1 are same, right. So, can I simplify this as W times of 2 theta 1 L by 3 plus 2L theta 1, okay, which will become W theta 1 8L by 3. Can I write this? So, I simplified this equation further in this form, W theta 1 8L by L. So, now you see I have internal virtual work in terms of delta, but here I have this in terms of theta 1. Okay. Let us convert this, which now become W theta 1 by 3 of 8L, which can be said as W by 3 8L, okay. You can see here theta 1 is alpha, we already said that, okay. So, I have set theta 1 as alpha, okay. Now, alpha and delta are connected, alpha and delta are connected by this equation. So, let us do that, which will now become W by 3 8L. So, alpha is delta by 2L, is it not? Is delta by 2L, okay. So, L goes away and this becomes 4. So, that becomes 4W delta by 3, that is my external virtual work. So, now you see external virtual work is in delta, internal work is also in delta. Let us compare this. So, external virtual work should be equal to internal virtual work. So, 4W delta by 3 should be equal to MP phi delta by 2L. Okay. So, now delta goes away, I can straight away find W as MP times of 15 by 8L, okay. So, now we have different values. Let us see what are the values we have. We have W1, which is from the beam mechanism, which was equal to 2 MP by L, sorry, beam mechanism 9 MP by 2L, 9 MP by 2L, which is 4.5 MP by L. We have W2 from the sway mechanism, which is here, which is 2 MP by L. Okay, it is 2 MP by L. We have now W3, which is a combined mechanism, which says it is 15 by 8L of MP. So, we must choose the least of all. Okay. So, now the true collapse load will be 1.875 MP by L, which is given by here. So, I have a frame loaded by lateral and vertical. These are the points A, B, C, D and E. This was the mechanism what we had. Which gave us the true load. So, we have hinges at here, here and here, is it not? So, now we say there is no hinge hit B. So, M at B is lesser than MP. So, we have to prove this. Is it not? Because we do not have a hinge at B. So, we have a hinge here. So, let us draw the bending moment diagram on the tension side. So, this is MP and again this is MB, this is MB and this is of course MP and MP and MP. I am drawing BMD on the tension side. So, I am just joining this. Okay. So, I want to find MB. So, if you look at this, MB will be actually equal to, let us say if this is W, there is reaction will be W by 2. Let us take the column AB and find out MB, which will be W by 2 into 2L. You know this is 2L, okay, into 2L minus MP. Now, if I say this W is my WC, let us say WL minus MP, which is 1.875 MP by L into L minus MP. So, I get minus 0.875 MP. Negative is due to a sagging moment and it is lesser than MP. So, no hinge is formed at B. Hinge will only form when M is equal to MP, is it not? So, we have proved it. That is how this problem can be solved easily. Let us take one more example and try to solve this. Let us say, I will say example 3. We have an unsymmetric frame both ends fixed. There is a lateral load W and there is a central concentrated load 2W which is at the center, and the capacities of columns and beams are same. Okay. So, let us say this height of the column is L and the span of the beam is also L and the height of the other column is twice of this. Okay. So, the question is find out the true collapse load. So, let us quickly see the degree of static indeterminacy for this problem. Neglecting axial deformation will be 4 minus 2, which will be 2. Okay, because we are neglecting axial deformation. So, this is A, this is B, this is C, this is D and this is E. right. So, we need number of plastic hinges as 3 to make it as a mechanism. So, we will start with the beam mechanism. So, we assume hinge at B, E and C. So, it is a beam mechanism. So, there is a hinge here, here and here. Okay. So, this is 2W and this is theta and theta and this is 2 theta. Okay. And of course, this displacement is del. So, the external virtual work in this case is 2W into del. The internal virtual work in this case will be MP into theta, this is at B, plus MP into 2 theta, this is at E, plus MP into theta, this is at C, which makes it as 4 MP theta. So, equating external virtual work to internal virtual work, 2W del should be equal to 4 MP theta, is it not? And we also know from the figure that theta is del by L. Okay, the span of the beam is 2L, please take it as 2L. Okay. So, theta by L, del by L is theta. Okay. So, substituting, two W into del should be 4 MP into del by L. So, WC in this case is going to be 2 MP by L, the first iteration. Okay. Let us go for the next one, which is going to be a sway mechanism. So, this is my frame. The frame is going to sway to the right. This point is A, B, C, D, and somewhere it is E, there is a load here, and now there is a lateral load here W. If I call this as delta and this as alpha, this is also going to be alpha, and this is beta, this is going to be beta. Okay. And we know this is 2L, this is also 2L, right. So, let us assume hinges at A, B, C and D. Okay. So, now the external virtual work is going to be equal to W into delta. The internal virtual work is going to be equal to MP into alpha, this is at A, plus MP into again alpha at B, plus MP into alpha, this is at C, plus MP into beta at D. So, which makes MP into 2 alpha plus 2 beta. So, we know external virtual work should be equal to internal virtual work by principle of virtual work. So, W delta should be equal to MP into 2 alpha plus 2 beta. Now, we know from the figure alpha is delta by L and beta is delta by 2L. Let us substitute that here. So, W into delta is going to be 2 times MP of delta by L plus delta by 2L. Okay. So, which will become 3 MP by L. So, now delta goes away, WC is 3 MP by L. Equation 2. In the first iteration we got 2 MP by L, now we have 3 MP by L. Let us also do a combined mechanism. Let us do a combined mechanism and see. Let us say this is my combined mechanism. I am going to assume hinges at this place, here and here. Okay. Let us say this is alpha and this is theta, this is 2 theta, because this is also theta, and this is beta and this is beta. Okay. So, let us say external virtual work is, okay, the loads are, this is W and here there is a vertical load of 2W. So, the external virtual load is going to be 2W into del, where this is del and this is delta, plus W into delta. Internal virtual work is going to be, this is A, this is B, this is C, D and E. So, MP into alpha, this is at A, okay, plus MP into 2 theta, that is at E, plus MP into theta, that is at B, C, plus MP into beta, that is at C, plus MP into beta, that is at D. So, one can say MP times of alpha plus 3 theta plus 2 beta. Now, for a sway to be happening, we can say, keeping this angle as 90, for sway to happen, delta should be theta, alpha should be theta, is it not, this angle and this angle, because then only this angle is 90. So, therefore, internal virtual work will become MP times of 4 alpha plus 2 beta. Okay? And we already know the value of alpha and beta, which we wrote here. Alpha is known and beta is known. Let us substitute and get the true collapse load. So, now I can say external virtual work should be equal to internal virtual work. Now, see here, alpha is equal to theta, is it not? Alpha is equal to theta. So, where alpha is delta by L, see here, alpha is delta by L, because this is L, whereas theta is also del by L, is it not? So, I can say these two are identical, am I right? So, the external virtual work is W delta plus 2W del, which can be written as 3W delta, that is external virtual work. Internal virtual work is going to be 2 MP times of 4 alpha plus 2 beta, MP times of 4 alpha plus 2 beta, and alpha is del by L and this is del by 2L. So, MP times of delta by L plus 2 times of delta by 2L. is it not? Which makes this as phi mp delta by L. So, equating 3 W delta is phi mp delta by L. So, I get Wc as phi mp by 3L. Okay. So, now this is the third one I have, which is about 1.67. So, now I have this is 3, this is 2 and this is 1.67. So, the true collapse load is the least of all, which is phi mp by 3L, and for a given cross section we already know mp, I can find Wc. Okay. So, friends, these are some examples where we have obtained very easily the collapse load for different mechanisms, combined them, then we got a taste of how to get the iterative mechanism about this and get the collapse load. So, as a summary, in this lecture we learned more examples of plastic analysis. We will also do one design application very quickly now. Okay, let us do a design application. Is a new example. We say I have a simply supported beam of size 230 by 450 in cross section. The beam is fully loaded. Till the central section is completely plasticized. The beam is subjected to a central concentrated load. What is want is demarcate the yield region. That is the question. Okay. So, the beam is like this. So, simply supported beam, central load for a span of 5 meters. The cross section is a rectangle of size 230 by 450. Take yield value as 250 megapascal. Okay. Let us try to find the solution of this. We know MP is going to be equal to Zp into sigma y, which will be shape factor into Zy into sigma y, which is 1.5 into 230 into 450 square by 6 into sigma y is 250, which becomes, friends, 2.9 into 10 power 3 kilonewton meter. Okay. For this problem, by the way, Wc, the collapse load, will be 4 mp by L. So, if I know mp, I can easily find the collapse load and so on, which will be 2.32 meganewtons. That is the load at which the beam will collapse. Let us also find out what is the yield moment of this. So, step number 2, let us try to find out the yield moment, which will be sigma y into zy, which will be 250 into 1 by 6 of 230 into 450 square, which will be 1.95 into 10 power 3 kilonewton meter. Okay. Let us draw the demarcated region. This is my beam, this is my bending moment diagram, this is my deflected profile. Okay. Here the moment is 0. At this point it is MP. At some sections, this is MP. At some section, this value is My. Okay. From a similar triangle we can find this. Can we find this? From a similar triangle, the span of the beam is 5 meters. So, we can say for 2.5 meter this is MP, therefore, for x it is My. I know MP and My, I can find x, which will be My by MP of 2.5, My is 1.95 and MP is 2.9 into 2.5, I get x as 1.67 meters. Okay, this is 1.67 meters. So, only this portion is trying to get yielded, remaining this portion is still elastic, okay, because up to this point it is My, right. So, now let us say this is my beam, this is my deflected profile, with the bending moment diagram as well this is MP here, this is My here, and this distance is 1.67, this is also 1.67 by symmetry. So, I can say M at 1.67 is My, which is 1.95 into 10 power 3 kilonewton meter. Can I find M at 1.8 from the similar triangle principle, which will be 1.8 by 2. So, I can find at 1.8, let us say I have a section here, this is 1.8. So, at 2.5 it is MP, at 1.8 I want to find this value. So, I can say 1.8 by 2.5 into MP, right. So, I can find this. So, 1.8 by 2.5 into 2.9 10 power 3. So, I can know this value as 2.088 10 power 3 kilonewton meter. So, can I this way find M at 1.9, M at 2.0, M at 2.1, 2.2 and so on, at M at 2.5 will be equal to MP, right, which will be 2.9 10 power 3 kilonewton meter. So, I have moment at different sections, okay, I have moment at different sections, I have computed them. So, let us also find the depth of elastic core. We know the equation, M is equal to MP times of 1 minus E square by 3H square. So, I can say M by MP is 1 minus E square by 3H square. By this logic, E square will become 1 minus M by MP times of 3H square, right. So, it will have a parabolic variation as E square, okay. So, can you now find what is the depth of elastic core at 1.67? How do you do that? It is 1 minus m at 1.67 by mp into 3h square. H is the depth of the section. So, it will be 1 minus m at 1.67 is 1.95 into 10 power 3. You can see here 1.95 10 power 3 by mp is 2.9 10 power 3, 3h square which is 450 square. So, I can find very easily this will be 450 mm, which is completely elastic at 1.67. See here, at this section it is fully elastic, is it not? That is what you are getting. Similarly, can I find E at 1.8, E at 1.9, E at 2? How can you do that? Because at all these sections I have moment at 1.8, moment at 1.9 I have here, see here 1.8, 1.92, I have all the moments. Can substitute here and I can find the depth of elastic section here. So, if I try to plot that, the plot will look like this. If this is my depth of the section, if this is the center and this is 1.67. So, it is 1.67 from here and it is 1.67 from here, and you see the hinge formation will be like this. So, this is how it is plasticized, and at the mid span it is fully plastic, it is MP. So, friends, this is how we demarcate the yield region. So, we have also learned how to demarcate the yield region, and we learned how to find out MP by iteration, not MP, sorry, WC by iteration. So, friends, in this lecture we learnt about the analysis and design. In this module we learnt about plastic analysis and design in detail. Now, we will move on to the second module, the third module, which is on stability of members. Thank you very much. Have a good day.